Hi, I am Burak Tokmak. I'm here to present my introduction to image processing assignment to Final Code. I will demonstrate the end results of my code and go over the functions themselves at the same time. When I run my code, first thing that pops up is the crop window for cropping. Uh, I used uh, I used mouse movements for cropping. To process mouse click events, I defined a callback function named mouse call. What this function does is if mouse left button is clicked and mouse is dragged across the screen, it drives a rectangle uh, area, and for cropping the image, I simply need to press the C button or Q button for quitting the image crop window. If you look at the function itself, this here checks to see if I press the left mouse button. This here checks to see if I'm moving the mouse while pressing the left mouse button, and this here uh, checks to see if I lifted my finger from the left mouse button. Uh, and what happens here is it checks to see if I draw the rectangle uh, like this or like this. Uh, and assign the end and start x and y values accordingly. If C button is pressed, uh, it will crop the image according to the size of the rectangle, like this. Uh, if I press the Q button, it will quit the cropping window, and we will present it with the main interface of my image edit tool. All the functions in my code other than the mouse callback function uses track bars to operate. For example, if I move the mirror track bar to 1, it will mirror the image like this. Mirror function does this by checking the value of track bar, and then if it's set to 1, firstly MP numpy array of zeros that has the original image height and width values, which is 520 to 520 is created, and for every pixel in for every pixel this equation is calculated, which is basically turns the image on y-axis by remapping the original image pixel values on the newly created array, and the resulting image is showed for the mirror operation. Resulted images here. For flipping of the image, same steps are taken with the mirror function. Only difference is the calculation that happens here, which turns the image on x-axis instead of y-axis. The resulting image then is showed for the flip operation. Result is here. For histogram normalization, first step is the flattening of the image to the 1D array. That happens here. This one-dimensional array together with the number of bins is sent to the getHistogram function. Inside the getHistogram function, array of zeros that have that have size equal to the number of bins value is created. After that, it loops through each pixel and sums up the count of pixels and returns it. Then returned value from getHistogram function is sent to the CumSum function. Inside the CumSum function, cumulative sum of the histogram is calculated. Then it returns the result. The returned result value from the CumSum function is normalized to be between 0 and 255, and casting to uint 8 form performed. Then it gets cumulative sum value for every index value in one-dimensional array and sets it as new image before finally reshaping it to its original shape and displaying it. Result of the histogram normalized function is like that. For brightening operation, firstly a variable named value that is to be added to the third channel of the HSV color space initialized. Then images converted to the HSV color space. Then each HSV channel is splitted after this limit value is created for preventing pixel values to go over 255. Then value is added to the third channel of the HSV color space. Then all channels are merged together. Then the resulting image is once again turned into RGB color space. Result of the bright image is like that. For darkening operation, all the steps are pretty much the same with the bright function, except for the value variable. Value variable is now subtracted from the third channel of the HSV color space. Result of the dark is like that. For rotation operation, if its track bar value equals to 1, it will rotate the image 90 degrees. If its track bar value equals to 2, it will rotate the image 180 degrees, and so on. For achieving this, I used my rotation function together with my angle function. This angle function takes the image itself and angle rotation degree as arguments. Firstly, angle function gets the image height and width values and find its center. After getting hold of these values, calculation of affine matrix of 2D rotation is performed. Then it obtains cosine and sine values from the rotation matrix, which is M, which is represented as M. Then using these cosine and sine values computes new dimensions of the image to prevent any cutoffs. Then it uses these dimension values to adjust the rotation matrix, and lastly it uses CV2's warp affine function to do the rotation on the image and returns the image for rotate function to use. result is like this. Oops. Şöyle. For inverse operation, image is converted to the grayscale, and then this grayscale image is subtracted from the value of 255 to get the inverse image. Result of the invert function is like that. For normalization operation, if track bar is set to 1, image is split to its RGB channels. Then these grayscale images were given to the CV2's equalize histogram function. Then all three channels are put together and resulting image is shown. Result is like that. That's it for the part 1 of this assignment. For part 2 of this assignment, first thing I did was creating two separate windows for effects and filters. To access these windows, all we need to do is set the related track bar to 1. For creating the two new windows, I defined these two new functions like that. This is the filters window. For applying black and white filter, this function gets each pixel's data from it as tuples using dot get data function. Then it iterates through the list of tuples and average each pixels RGB value to one single illumination value. Resulting array is sorted on a list that's created in here. A new image is created using a Pilgrim's image.new function in L mode, and Pilgrim's .put data function to build the new image from the list of pixels in the list. Then new image is converted to an NumPy array to be displayed. This is the result of the black and white filter. For applying the sepia filter, I need to multiply my image matrix, which contains integer values, with the sepia matrix, which contains float values, as you can see. So for avoiding any potential data loss, I made conversion from integer to float. After multiplication, I normalized the values to avoid going over 255. Then the result is converted back to the integer and shown. Result of the sepia filter is like that. For warming filter, I created these two functions. This create lookup table function returns a 256 element list that contains the interpolated fx values for every possible value of x. In the warm filter function, two curve filters is defined. One is for increasing all pixel values of a channel, and one for reducing it. Then image is split to its RGB channels. Then for warming filter, R channel pixel values are increased and B channel pixel values are decreased. Then all channels are merged to form the RGB image. Then this image is converted to HSV color space and split into its HSV channels. Then the value of the S channel, which is saturation, is increased, and the HSV channels are put back together, then converted back to RGB color space before displaying. Result of the warm filter is like that. For cold filter, almost all steps are the same with the warming filter, but there are some small differences between them. In cold filter function, R channel pixel values are decreased and B channel pixel values are increased. Then after conversion to HSV color space, pixel values of the S channel decreased and the HSV channels are put back together, then converted back to the RGB color space. Result of the cold filter is like that. For Gingham filter, I defined these three functions. In Gingham, when track bar is set to 1, predefined values for hue, saturation, contrast, and brightness are sent to their corresponding functions to perform operations. Firstly, image, hue, and saturation are sent to the hue saturation function. In this function, image is converted to the HSV color space, then hue and saturation channels are accessed. Then for both of these channels, values in the channels are limited by using dot clip functionality of NumPy. After that, image is converted back to the RGB color space and returned. Then this returned image together with contrast and brightness values are sent to the brightness contrast function. In this function, image contrast is changed by multiplying pixel values with predefined alpha value. Then brightness of the image with the change contrast is changed by adding pixel values with the predefined beta value. Then resulting pixel values are limited using .clip function. Lastly, image is cast to uint 8 before return. Result of the Gingham filter is like that. For FX, we have these effects. For cartoon effect, I created these two functions. When track bar is set to 1, image is converted to grayscale, then inverted by subtracting our gray image from the value of 255. Then Gaussian blur kernel, which is predefined, applied to the inverted image. Then resulting image given to the CV2's adaptive threshold function to get hold of the edges on the image. Then original image is sent to the color quantization function to be stripped from its colors. Color quantization function achieves this by applying k-means algorithm. Resulting image is returned back to the cartoon function, and bitwise AND operation is performed with the edge mask. Then resulting image is displayed. This is the result of the cartoon effect. Embossing gives the illusion of depth by emphasizing the differences of pixels in a given direction. In my use of the embossing effect, I selected this direction to be bottom left side by using an array containing ones in its bottom left side as a kernel. Then this kernel is convolved with the image, and addition of a value 128 is done to all pixels for the emboss effect. Result of the emboss is shown here. For pencil sketch effect, I created these two functions. When trackbar is set to 1, image is converted to grayscale. Then image is inverted. After that, predefined Gaussian blur kernel is applied to the inverted image. Then both blurred image and gray image is sent to the merge function. In merge function, blurred image is divided by grayscale image, and after making sure that the resulting pixel values are between 0 and 255, the result is returned to be displayed. Result of the pencil function is like this. For sharpen effect, when trackbar is set to 1, the original images convolved with the predefined sharpened kernel, and resulting image is returned. This is the result of the sharpened effect. And lastly, for vintage effect, when the trackbar is set to 1, the original image is convolved with the predefined Gaussian blur kernel, and resulting images returned. This is the result of the vintage function.